The way there always seems much longer than the way back. Because on the way back it's all very familiar and things, it seems like it's quite bizarre, but perception-wise it seems like heaps shorter. Well, you'll find that second semester, all the other semesters will seem heaps shorter and easier than this one. And this is pretty short, yes. It's only 12 weeks. You can't see? Okay, that's all right, because I'm typing in a password. But I'll... Let's go. Off. Off. Down. Here we go. Da, 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 da. Nearly there. Shum. In Lab 12, you can have your exercises marked in Lab 13? No, that's not true. Is that what it said? That was just someone being funny. Okay, let's go. Is everybody ready? Oh, thank you very much to Brett for putting up the Noin Ziggium picture. It's awesomely good. Where are you, Brett? Wave at me. Is Brett here? Brett Phillips? Where are you? Wave, wave. I can't see you. Oh, there you are. Oh, awesome picture. Thank you very much. Made me laugh. I posted it onto the thing. Now, oh, I've just lost that page. How did I do that? Professionalism and ethics. No, that's not us. That was last week. That's so last week. Let's go this week. Here we go. And I'm looking for Richard's bullet points. And now we're in today's lecture. Okay, so finish off what we were doing last week. At the very end of last week, I was talking about Cartier Bresson. And I showed you this book, Henri Cartier Bresson. And I said, why did I show you Cartier Bresson? A, because everyone should see Cartier Bresson. But B, more importantly, because I think it's an answer to the question, what makes a good programmer? I always like answering a question with another question, you see. Because I like you sort of to answer them yourselves. And so what makes a good photographer? Well, I don't really know what makes a good photographer. But I know this guy is a good photographer. Because when I look at his photos, I'm deeply moved and humbled. And I can see he's so much better than me. So let me talk a little bit about what makes a good photographer, and maybe you can use my answer to that to work out what makes a good programmer. When I started taking photos, as I mentioned before, I bought a nice camera and I took some photos, and my first roll of photos I got back were completely crap. And even I could recognise they were completely crap, and I was really disappointed. I almost wanted to get my money back for the camera, because I expected buying this piece of technology would let me take brilliant photos. So I put lots of thought into thinking, but you know, before I tell you how I made my photos a bit better, if that first roll of photos had come back and they'd been brilliant, what do you think would have happened? I would have stopped taking photos. There's no much fun in doing something that's really easy, but because I got that first roll of photos back and they were crap, but one of them was okay, maybe. Took a little one of my dog, it was okay. But because they were basically crap, I thought, this is no good. How come I can't do this? And I started putting a lot of effort into trying to improve taking my photos. And it was a really worthwhile challenge. And it took me a couple of years before I took photos that were even passably good, and certainly my photos aren't good. And because it was hard, I worked really hard at it. And it was really satisfying as my photos, as I could see over time, my photos got better and better. And it was a difficult thing to do, so I really like that. Now, to take good photos, I don't know what makes a good photo, but I can tell you what makes a bad photo. First of all, you've got to get the techniques all right. Like, you can't be blurred, and you can't get the focus wrong, and the exposure's got to be reasonable. So there's all the sort of technical stuff you've got to get right. And I would say that's a bit similar to knowing the syntax of C. You need to know C in order to be able to write a program in C. Knowing C is not going to help you write a good program in C, but not knowing C, you're stuffed. So you need to know this technical stuff. And how do you learn that? Well, how do you think I learned to get the focus right and the aperture right and you know, not wobble the camera? And how did I learn all that sort of technical technique stuff?
You read the manual?
I read the manual. Yeah, I read it. And I went to a lecture at uni, and someone spent a whole semester talking to me about how to take a good photo. And that was all interesting. But I practiced, yeah. I just went out and I took hundreds and hundreds of photos. In those days, that cost money. These days with digital, it's free. And I practiced and I practiced and I practiced. And after a while, it got to the case that I could focus without thinking, and I could pick the light levels pretty quickly without thinking, and I didn't move the camera, and I picked more or less reasonable speeds, and I composed the scene, and I just did all the sort of technical stuff, the craftsmanship. I got that right. And I thought, okay, my photos are okay. But I looked at them and they were still not good photos. And I realised a photo has to have more. And I spoke to a person who's a cinematographer. And he opened my eyes to a whole new world. He said, well, your eye travels across the picture. So you have to think of the path the eye takes when it sees the picture. And you have to get the right mix of light and dark so it doesn't look too murky and too dark, and it doesn't look too flat and washed out. You've got to get it fairly contrasty. And he talked about the amount of contrast you've got to get. And then he talked about this natural transition of moving left to right, and then special focal points in the picture where apparently your eye is really happy if it sees important things at certain points, you know, like the rule of thirds and things. And he said these are just rules and you can break them, and the good photographers do, but if you follow these rules, they tend to be good. So I started thinking of these higher level principles, things to make photos that were more compelling. And my photos became more and more compelling, and then I still wasn't happy with them. And then I started to realize, I started to think, what did I want to get out of a photo? When I was taking the photo, what was the point of the photo? And I realized that normally I was interested in people. So when I was taking a photo, I wanted to somehow say something about the person or reveal something about the person, or have you make the watcher start thinking about the person. And I started thinking about the composition of the photos and all these higher level skills. Now can you see, hopefully, there's not much of a jump to see that there's really not much difference between that and computing. Yeah. Computing, the first couple of programs you write are crap. Thank heavens for that. If you came along here and wrote a program, we said full marks 10 out of 10, the first thing you wrote, you think, phew, what sort of degree is this? Well, some people like accounting. Did someone say accounting? Infosys. Some people like degrees that are very, very easy, where you don't learn anything and you're really good at everything right from the beginning. I guess that's okay. Has anyone read Brave New World? Arts is not like that. Brave New World. Oh, you had to study it, did you? I can tell from the moans that it wasn't pleasurable reading. Brave New World, the dilemma is this guy wakes up in the future everyone's happy and everything's easy. And if you're sad, you take drugs to make you happy. But everything's so easy that it sort of has no value. And it's this agony that this guy goes through. I think his name was John. And he's the agony that you as a reader go through as well, because I don't think Aldous Huxley ever raises this question explicitly, well maybe he does, is it better to be John the Savage, who's not happy all the time, but who's feeling real emotions and intensity and ups and downs and living life as it's supposed to? Or is it better just to take drugs all the time and be really happy? Woo! And the lovely thing about it is it's not really clear either way. You could go both ways. You could take this easy life and it would be absolutely fine and the drugs wouldn't make you happy and everything. So it's not, you know, on the surface of it really bad. And the other way, you know, it's like, I think it was John Stuart Mill said, is it better to be Socrates dissatisfied or a pig satisfied? What would you rather be? Yeah, it's this interesting question. So anyway, I decided I wanted to do something challenging. So computing was good. You have to learn the technical stuff first, but that's not enough. So hopefully this is the position you're all in. At the start of the course, some of you knew the technical stuff already. And you were at various levels of being able to take photographs. Some of you hadn't even picked up a camera before. So you had to master this sort of practical stuff, and you could only do that by practicing. And I sort of lied to you. Because remember I said by halfway through the course, it'll be okay, and you'll have caught up. And by the end of the course, everything will be fine. Well, you sort of have caught up, and everything sort of is fine. But the lie is in this sort of implied, and then you can rest and relax. I can't believe you fell for that. Because to master anything in your life, no matter whether you're an A, B, or C at the beginning, the only way you're going to get really good and get really satisfied and do beautiful, amazing, remarkable things is to constantly work at it. Not in such a way that it kills you and you don't see your friends and family, but in such a way that you never relax completely. You've always got to be pushing yourself a bit. So I suggest every now and then, set yourself a challenge and do the challenge in programming. I don't care what it is, but if you're doing a boring programming course in the future and you think this course is so boring I can do it like anything, well then do it left-handed. Like that scene where, remember where Darth Vader says to, what's the guy? His lord? Well, Sauron. Darth Vader says to Sauron, Sauron says, you must fight Obi-Wan Kenobi. And Darth Vader says, I will do it left-handed. Do you remember that? It's the same thing. It's just rising to the challenge. Okay, so constantly test and challenge yourself. I'm pretty sure I got that right. Okay, shh. Now, I have some shh. Because it's so hard to articulate what makes a good photo. When I showed you the photos last week, remember I was flustered and moving around, and to me it was all this pleasure looking at these photos. But it was very hard to articulate because what made them good was they were technically good. At every level they were good. They were technically good, they were compositionally good, their meaning was good, their message was good, they were visually pleasingly good, they made social commentary. They were good at every level. I didn't even know where to start. So I thought rather than knowing where to start, I'll just show you one or two of his pictures. Because I found a gallery that sells prints of them, but sadly the ones I like have all been sold. And they seem so cheap. Look at this. This is his most famous photo of all time. This is just really cool. It's a man just outside, I assume it's a train station. Garmin's train station. He's just like stepping off and you wonder, what was he doing? What was he thinking? Where was he? See, he's about to step into that puddle. There's just enough ripple there that you know it's just like this perfect, he's caught that exact moment. And you're thinking, what's going through the man's mind? It really is a frozen moment in time. This is just an absolutely amazing photo. Some other ones of his. All the India ones are amazing. I won't go into them, but they are quite amazing. Here's one of Mexico. Just people, and I love people. So watching this, you just think about the people, and you see it's good at every level. You see the random location of the people on the ground is sort of mirroring the random distribution of the windows in the building. You know, there's this sort of arbitrariness, and everyone seems disconnected, but yet you're interested, and you're drawn to this strange man walking across, and the balance of light and dark, and action and passive. It's just very interesting. This one here. One circle makes you look at the other. Your eyes eventually ends up, and all you're looking at is the little boy. Or girl. Yeah. It's a girl, you reckon? I reckon it's a boy.
It's a man.
It's a man? He's got a beard. He doesn't have a beard. That's not a beard. What are you talking about? You could have sworn it was a beard. What about this one? He was just there when the Dessau camp was disinterred and everyone was freed. He caught the exact moment that one of the prisoners recognises the informer that turned her into the Nazis. Absolutely fantastic. So, he's just this amazing guy. And now I've got some other photos I want to show you. And these photos are actually crap photos. Let's look at them. Some trees. I took a photo of trees myself. I couldn't find it this morning because things were a mess. So I hunted around on the internet and I found some pictures of trees. Notice they're all crap. But look at these trees. Can you see? Trees. I've got 3 photos of trees. 1, 2, 3. Can everyone see? Why am I showing you these pictures of trees? Because for me, this summarises sort of what computing is about. What problem solving is about. These trees are planted in a grid. Can you see that? At my old uni, there was a quadrangle with trees all planted in a grid. And I used to play this game at the uni all the time because it just blew me away. If you stand sort of in the middle, but not on a grid point, this photo's been taken on a grid point. What's the person thinking? But if you stand in the middle, not quite on a grid point, and you go like this, and you just look straight ahead, just in this little tunnel, and you go like that, and you slowly rotate around, then when you're looking down the row, it looks absolutely symmetrical, and the order and the pattern is revealed, and it's very clear that it's trees in a grid. And then as you slowly swing around, it gets a bit more jumbled and crazy, and then suddenly it looks like randomness. It looks absolutely disordered, and you cannot see the grid pattern at all. And then as you hit a diagonal, boom, the grid reappears and re-emerges. And to me, that's what problem solving is all about. You've got a problem. There is an underlying, simple, beautiful way of looking at the problem. And if you look at it one way, you just see chaos. And if you just pick the right way of looking at the problem, suddenly the problem leaps out at you and you see the simplicity inherent in the problem. You could write the messy program to solve the problem viewed that way, but if you just shift your point of view, you suddenly think, oh, of course. Does that make sense? It's quite amazing. I used to do that all the time. It was quite a weird thing to do. So there's actual documentary film of me just rotating round and round like this. Okay, so now let's do a review of the course and where we're up to. I think that's all we had to do. Week 1. What I've done is I've gone through all the lectures that we've gone over the course and I've just quickly written down what I think are the important things we've done. Here's a summary of the whole thing. Week 1. I started off talking a lot about the fact that this course was about hardness and what was going to be hard, and it perhaps wasn't what you thought was going to be hard. And I suggested, and now let me say it explicitly, that the key to success is somehow managing yourself in how you deal with this hardness, how you deal with your emotions and how you deal with your motivation. You will want to give up over and over again. You must never give up. And if you give up, you must not then think everything is hopeless and stay giving up, but you must pick yourself off the ground and try again. Now, I said at the beginning of the course, this is what the experienced programmers know already, and this is their real advantage. Not the technical stuff they know about how to focus the camera and things like that, because anyone can pick that up. What they know is if they stick at a problem and it doesn't work, if they keep working at it, eventually they will get it. You guys didn't know that at the beginning if you were starting to program, but hopefully you know it now, that you've attempted enough programs and you've known that eventually you can get there. You don't always get there, you have failure, but yeah. So for me, computing, the hardest in computing is this mental state. It's not about the domain of computing, it's really about managing yourself. Okay, if you're an A person, then I hope A people were the ones that had never programmed before. Then looking back over the course, I hope you now realise you have got some skills that you didn't have before. Not just some skills, you've got a bloody lot of skills you haven't got before. You know C, you can do all sorts of interesting and bizarre things in C. You can write programs and you can go from a problem to a program. It's absolutely amazing. So I want you to look back on what you have mastered if you could never program before and feel very proud of yourself, because I'm very proud of you. I think that's fantastic. And C people, even if you could already write a program, I hope you've gone over this course and this course has been a time of reflection for you. So you have thought not only, oh yes, I've used abstraction all my life in programming before, but how maybe now you're thinking, and now I think about abstraction and I understand why it's good and I understand why I use it and I can see the implications of using it. So hopefully you've reflected on things and you've learnt the you hopefully already could write correct code and now you've started to write beautiful code is what I hope. Or at least you can appreciate the difference. I guess we all strive for beautiful code. We never exactly get there and gee, you know, that's sort of good. I like that. All right, so what are the stages that you're going to go through in your time at CSE? This is the other thing I mentioned. I reckon there's 3 sort of stages and we try and hit them in the first 3 courses. First course is about craftsmanship. That's this one you've just done. The second course is about the science of programming. That's what you'll do next. And the last course, Comp 2911, is about design, about becoming a designer, about being a person that designs beautiful programs. So this is the path you're on. So I hope you continue. And we've seen a taste of all of those things in the first course, but we've mainly focused on craftsmanship. I did give you a little piece about RSI, and do you remember that? I said if you remember only one thing, remember this. What was it? Oh my God.
Don't get it.
Oh, don't get RSI? That was not what you just made that up now. That's, you're going to do in the exam. How to add up numbers? No, that was the one formula you had to remember. That's the one thing you have to remember too about RSI. What's that? Try it and see? No, no, no. Practice, practice. No, no. The one thing about RSI was 00110111110111. What's that?
Differentiate your tasks.
Yeah, yeah. Change. When you're sitting down for 5 minutes, move. If your arm's been in that position, put it to this position. Stand up and stretch. Move your angle, move your screen, move everything. Never do anything for too long without change. What was the advice that past students gave? Start early. Tomorrow, on Wednesday, I'm going to ask you guys all to give a piece of advice to next year's students. So I want you to think about what advice you'd give them. But I hope you took on board their advice of starting early. Their one biggest regret was they didn't start early enough. So at the end of each of their tasks, just as they were getting to the interesting bits, they had to hand it in. Then we started to look at the structure of a computer. And we started from transistors, and I showed you basically what a transistor, we had a switch-like view of how a transistor behaved. I then told you that you could put transistors together to make chips, and we looked at a way of making an AND gate and an OR gate using transistors and also a memory cell. Do you remember that? Then I told you, but we didn't do it, how you could put gates together, that you could put gates together to make a microprocessor. But we didn't do that. Though we saw a little bit of that for fun about a week or 2 ago. We'll see a little bit of that for fun today. It's not part of the course. Putting the gates together to make a microprocessor lets us program a microprocessor. And you program a microprocessor using a language called machine code. And we started off with machine code rather than starting off with C. Why do you think we did that? So you understand, yeah, essentially that's the perfect answer. So you can understand some stuff about C. What things about C does programming in machine code let you understand?
It lets you understand how the stack works, it lets you understand how variables work.
It lets you understand how the stack works, how variables work. Can I summarize all of that by saying it lets you understand how memory works? It really lets you see the physical realization of memory. And C depends a lot on memory. And unlike in most modern languages, which hide the memory from you, and you deal with variables and you don't have to worry about what they look like in memory, in C, because of pointers, because of stacks, because of arrays, because of pass by reference and pass by copy, because of all of that stuff, and of
Strong typing.
they have strong typing, yeah. But because C doesn't have strong typing and you can write something out as a series of bits and claim it's a number and read it back in and claim it's a char, do all sorts of crazy stuff like that. We figured you really needed to understand physical memory. So we started this stream of machine code. And then we talked about the language C. I'm now at the very end of that long line. When you write a program in C, does your chip understand C? No. So what does your chip understand? machine code. If you're programming on a Mac or programming on a, what have you got here?
Linux.
A Linux, a Dell thing? Okay, so the microprocessor in here is an 86 processor, an Intel processor. So all the programs you're running there are actually in Intel machine code. But they were probably written in C. So how do they get from C to Intel machine code? Something called a compiler. So we looked at what a compiler was. GCC, the compiler takes C, spits out machine code. I must admit, we were very tempted at the start of the course to teach you assembly based on x86 assembly. Because then we could have done neat things like you could have written a program in C, we could have compiled it with GCC, we could have got that .o file that it produces, and then we could have opened it up and looked at it and you'd have seen all the machine code inside it. And so you could have seen, you know, got this whole view of the whole picture. But instead we start off with a really simplified machine code, the 4917. Why do you think we started with the 4917 rather than doing the x86 machine code? Yes. What's that?
x86 sucks.
x86 sucks. Yes? Is that what you're going to say?
No, I was going to say so that we could build a complex instruction set and then understand why you would build that up.
So both answers are the two reasons. Reason number one, well, what were you going to say?
I was going to say, so you can go through the process that the people who...
Oh yeah, that's what he just said. Yeah, that's right. So reason number one was we wanted you to go through the whole process that a microprocessor goes through as it evolves over time. Because if you see a modern microprocessor like the x86, it's way complicated. If you looked at it, it would just really freak you out if I gave you all the charts and tables to do with it. You'd go, what? I don't understand any of this. It's all horrible. And if you did understand it, it'd be just sort of by memorizing and whacking around at it. You wouldn't necessarily understand the shape and the structure and why the things are there and how they got them and so on. So we thought we'd do this thing like sometimes, there's a phrase for it, but I can't remember what it's called. Etymology follows bibliology, phonology or something. Does anyone know what that is? This idea like that inside your womb, as the baby's growing, it looks like all the different things that man looked like as man was evolving. Yeah, so it looks like a little a protozoan, then it looks like a little sort of fishy thing, and then it looks, you know, and there's this idea, we don't think it anymore, but it was that somehow evolution was being reproduced inside. And there's a phrase for this sort of fallacy of thinking that, and it's something like phenomena follows phenomena. Yeah. In other words, the way things grow follows the way how they got there. And so it would be fun, I thought, to sort of do that. So we could slowly teach it and we'd let it evolve, and as it evolved you could see the reasons behind the evolution to get to the final one. And the other reason, of course, is that the x86 language sucks, so we didn't even end up with x86, so we started to get a bit close to it. It's so big and complex that it's just freaky. And it's there because, do you remember each week when we asked you to vote on changes, we usually ask something like, should we change what we've already got, or should we make everything backwards compatible? And do you remember at every single point except the last, you guys voted, let's keep it all backwards compatible. Why did you want to keep it backwards compatible? What's easier?
To write the same code.
Yeah, to program. If you can already program on the old one, the new one, even if it's a disgusting mess, is only slightly more messy than the old one. If you did understand the old one, you can understand the new one without much work. Also, you can use the old code on the new one and everything works. You don't have to rewrite everything. So there's all these sort of convenient incremental reasons for not changing. It's like a frog in water as you slowly heat up the water. Yeah, each increment, it's easier to stay in the water rather than to jump out. But sometimes you can get to an end position where if you thought about it sanely, you'd think, I don't want to be a frog in boiling water. Okay, so what we did was it got more and more complex, and that's exactly what happened to the x86. Because of backwards compatibility, for marketing reasons, of course, x86 has never shed any of the early dumb ideas it has. It's just added new ideas to them. So it's like this big mess of a committee. Of a boiling frog. It's the boiling frog chip. That's what we call it. So I couldn't in the end inflict it on you. Now someone, I think it was, who was it? Wave at me. Who was it? Someone wanted me to teach you x86 assembly, and I was going to do it in an extension lecture, but we ran out. It was, I can't remember who it was. He's not here. I'll remember his name. No. Anyway, someone, so I was sad we didn't get to do that. But you don't worry, you will see x86 assembly language sometime soon. But it would have been fun for us to do it, and we would have done an extension lecture had we had a few more extension lectures. Okay, so we started on the 4917, which was very simple. It was so small that you could write the whole thing on a scrap of paper. And I wanted it to be so tiny you could keep it in your head and just think about it all the time. Now, a lot of you I know, at the end of today's lecture, when I go through revising the whole, when we just touch on the highlights of the course, as we've gone through the whole course, We'll then have another lecture on Wednesday, and that'll be the very last lecture of the course. In that lecture, I'll talk about the final exam, and I'll also talk about studying for the final exam, and I'll talk about how we're going to have review sessions and so on and so on and so on. And I just know, at some point I'm going to say, you guys tell me what you would like covered in a review session. And I just know what's going to be the single most popular thing that people want covered. Machine code, boiling frogs. Everyone's going to say, oh man, I didn't get that machine code. I put it out of my mind early on, and then it just kept staying there, and it freaked me out more and more each week, so I looked at it, like my email. I haven't looked at it for a couple of weeks, and now it's so scary I can't even think about looking at it. But I will look at my email, and you will look at the machine code, and we will all get it. It will be okay. So we'll talk about how we're going to review machine code. Then we started introducing C once we'd seen the machine code, and we looked at the fact that the compiler happens in 2 steps. The first step is called a preprocessor. That actually rewrites your program before it compiles it. And the preprocessor, as far as we're concerned, does 2 things. Hash include, which means it embeds other files inside your program. So if your program says hash include stdio.h, the preprocessor files a file called stdio.h and literally inserts it into your program at the very spot where you've said hash include, before compiling. And the other thing it does before compiling is everything that's hash defined, every constant that's hash defined, it replaces with what you've hash defined it to. That's a preprocessor. And when we looked at our first C program, which was a Hello Australia program, do you remember that one? We noticed that it had a comment in it. We talked about comments. And this was sort of like almost the beginning, it's like emblematic of the course. That the first thing we talked about when we looked at the program was not how argc, argv works and all that sort of stuff, though we did get to that eventually a few weeks ago. The first thing we looked at was, what does the program do? What do we think of it as a reader, as someone looking at the code, and what helps it make it clear to us and what helps make it confusing? And that was comments. So we started off by looking at comments. And we played the game of trying to work out what the program did just by looking at it. And if you can do that, it sounds like a good program to me. If you can look at a photo and understand it without me having to stand up and tell you about it, that's a great photo. If I stand up and tell you all about the photo and you think it's a great photo, well, it's still okay, isn't it? But it's not as good as if it's self-explanatory. Wiki notes. Oh, that was the end of week 1. That was a fairly long week. Week 2, we started talking about this notion of wiki notes. And I said, guys, I'm going to write something I call the official notes each week. And it's down to each tute for each different week, and there's an allocation of which tute does which week, to take notes over what we actually say in the lectures and put them up somewhere called raw notes. And at the end of the course, either the tutors or me are going to go through all the raw notes and mark everyone's effort in putting the raw notes up. And using the raw notes, you guys collectively can write a nice set of notes that we're going to call the nice notes, which summarise what happens into the course. So, flagging you now, we're at that time of the course. It's now time to start thinking about the nice notes. And as you study and look over the notes, if the nice notes don't look nice, if in fact you think they're crap notes, or what's the opposite of nice? Naughty notes. Naughty notes. That's very good. So if there's naughty notes, can you chastise them and correct them? So yeah, start whacking stuff in there, and we'll talk a bit more about how I'm going to print that out for the exam later on. You get to take all the nice notes in, as long as they're not like 1 million pages long. And comments. Okay, wiki notes. Then we looked at Boolean expressions. So that was and or. Remember, and is double A and or is double vertical bar. And we looked at true and false. And we talked about how they're stored as 0s and 1 in C. And we looked at assert. Oh, I was going to teach you assert. Actually, I let it slip a couple of weeks. But let's pretend I did talk about assert, because it's neat to put asserts in. And asserts just test. If you give it a Boolean expression and the expression is true, the assert's happy and everything happens normally. But if you give it a Boolean expression and the expression happens to be false, then the assert chucks a wobbly and the program terminates and a helpful error message is printed out. And that's very nice for testing your code at runtime. Of course, it's better to get problems out before runtime. And then we looked at some simple programs, and even before we spent much time writing simple programs, I harped back to this theme that I know I've kept going on and on about over the whole course, that really our biggest source of errors is ourselves. And the biggest problems you're going to have when you write programs are going to be the human errors introduced into the programs. If you're in a team, you'll be able to blame it on your teammates. And that's one of the reasons for working in a team. But if you're working by yourself and your program has errors, all you can do is blame it on Microsoft. But it's human errors that are going to give us problems at every time. And maybe we should look at ourselves a little bit. Okay. And then we looked at, gee, how do we even solve problems? And we looked at there's sort of how you solve a problem is a big open question. No one really knows. I teach a lot of primary schools. I was teaching there last week at a little tiny primary school and just doing a guest lecture to the kids on maths. And instead of talking about maths, we just did problem solving. And I was trying to get them to think about how they solve problems. And they didn't know how they solve problems, and the teacher didn't know how they solve problems. No one really knows. But we know there's a whole lot of thought gone into how people can systematise solving problems. So given a problem, if you're stuck, so you can sort of do something productive rather than just spin your wheels. And the first technique I gave you in the course, or that I mentioned in the course, I didn't give it to you, it's already there, the universe gave it to us, is called top-down. And the idea of top-down problem solving is when you see a problem, instead of thinking of all the little details and worrying about them, you work out, you ask yourself, what is the biggest, most important part of this problem? And how could I solve that? And you try and solve that by reducing it to slightly smaller problems. You don't try and solve it completely, you just try and solve it by reducing it to smaller problems. So how can I take over the world? No, that would be a crazy example. How can I what?
Take over the world that isn't Australia.
Take over the world that isn't Australia. That's a more patriotic example. How can Australia take over the world? That's a military secret. I can't tell you that either. But yeah, how can you do some problem? I've got a big problem. I want to bake a cake. All right, that's my problem. I want to bake a cake. Got to bake a cake. That's my big problem. How can I do that? Easy. Find a recipe, work out the ingredients, buy the ingredients, assemble the ingredients. 4 steps. Done. Now I know how to make a cake. Some of you straight away when I said how do you make a cake, you're probably thinking, oh, you need to whisk the egg yolk without mixing the butter into the thing. All the details, don't think about them. Just think, what are the big steps? And then you think, oh, I've got to find a recipe first of all. Find the recipe. Don't worry about any other problems when you're solving the find the recipe problem. And then work out what the ingredients are. That's an easy problem. And then buy the ingredients. Well, everyone can do that. We know how to go to a shop. And then assemble the ingredients. That might be the hardest part. We might have to break that into subparts as well. Prepare the batter. Then mix the batter, and then cook the batter, maybe. Maybe we break it into 3 problems. That's top-down. Top-down is not worrying about things and freaking out, but instead noticing that every big problem can be solved in terms of slightly smaller problems and deferring all the grief as far as you can. That's bottom, top-down. And I sort of mentioned that when writing programs, we tend to, left to our own devices, use an alternate way of solving problems, which is called bottom-up, where we straight away think of all the details and start writing lots of small components, and then we try and assemble those components together to produce the solution. That's bottom-up programming. It rarely leads to pleasurable outcomes. It can, if you're really smart and the program's really small, you can do it. But in practice, it doesn't lead to pleasurable outcomes because the bits you make, thinking, oh, I'll assemble these bits to make a car, at some point you've assembled them all and you're starting to put them together and one bit doesn't quite fit in with another bit and you've got to patch and fit around it and make adjustments and compensations, and you don't want to throw away the wheel you've already built, so you build a wheel adjusted, as, you know, all sorts of, you do compensatory things. Rather than coming up with a nice, clean, perfect wheel, if you've built an imperfect wheel by mistake because you didn't really understand its role until you got to the point of assembling it all together, then you don't want to throw away the imperfect wheel, so you think of ways of patching around it and fixing it up. Does that make sense? And then you end up with a car with wheels all different sizes that still can drive for some reason. But it's an ugly car. Okay. So bottom up, we don't really like. And the other point I wanted to point out about, and again has been a theme in the course, is testing. That when you think you've solved a problem, you've probably, due to human beings what we are, you've probably not quite solved it correctly. It's probably got some problems in it still. And if you don't test until the very end, it's very hard to know if the thing's safe or not. So if I'm building the harbour bridge, I could just build the whole thing and then think, is this bridge safe or not? And then what could I do? I could crash some boats into it or something and see if it broke. But I don't think that's a very good way of testing the harbour bridge. I think a better way of building the harbour bridge would be, as I ordered each bolt, to test each bolt first before I put it in the bridge. Or if testing damages a bolt, test a sample of the bolts. And then when I get members to weld together, I would test the members or random members. And as I did each weld, I would do tests on the weld. I would test as I go. And then I'd know each step was building on a solid previous step. And at the end, I'd be reasonably confident the bridge was okay. Yes?
Do you know how they actually did test the harbour bridge?
How did they test the harbour bridge?
They just got all of the train carriages and put them on the bridge, as many as they could, and watched whether it collapsed or not.
Oh, that's so cool. They still do that test every day. Did you hear that? The test was they got all the train carriages and put them on the bridge, as many as they could fit on, and to see if it could collapse or not. But I put it to you, that's probably not the only way they tested it. That's probably a really good test to do at the end. I would do that before putting people on. I'd put a lot of weight on. But I would hope that they tested well. That was built by engineers. So you can be sure, actually, that it was done properly, because engineers are actually, I know we're fallible as people, but engineers are pretty close to the infallible end, not because they don't make mistakes, but because they're obsessive about checking and testing as they go. So I'm sure they tested all the bolts and everything as they went, as well as putting the train carriages on at the end. Okay, so this was like, I hope you can see now, this is like a microcosm of the whole course, isn't it? Because these same themes came back each week, each assignment. And then I talked about, gee, you need to learn these skills. You need to learn how to focus and things like that. And I sort of, I compared it with some skills that I wanted to learn over the same period of time. I wanted to get fit. You guys want to learn C. And we sort of looked at how it was really the same thing we both had to do. We both had to do a lot of practice, and we both had to think about what we were doing and correct our behaviour as it started going off the rails. And finally, I mentioned it's not a course on C. If you want a course on C, just get a book on C. This is a course on programming, and we happen to use C. Yep. So you could easily teach yourself C by C for Dummies, or C in 24 hours, or Control Data C course, or anything. But that means nothing, because in the future there'll be different languages. We want you to learn skills, not facts. Does that make sense? If you just learn C and C's replaced, what do you know? Nothing. If you knew all about steam trains, just because you memorised all the bits of the steam train, but you didn't understand engines, then when steam trains are replaced by diesels, you're screwed. But if you really understood engines, and you understood how steam trains worked as an example of engines, when they replaced them with diesels, it didn't make any difference at all to you. Though it was terribly sad. Okay. And then finally we introduced task number 1, which was on software piracy, as you might remember. Another theme in the course. Yeah. It was I'm pretty sure it was on software piracy. Then we, the next week, oh no, we're still in week 2. Gee, it was a long week. We improved the chip a bit, and we started to talk about an interesting concept called side effects. Let me make that bigger for you. And side effects was something that kept coming up. And actually, for those that came to the extension lecture, where we talked about the Turing test, side effects sort of made difference in terms of that example too. Side effects are things that don't affect the extensional behaviour of a function. We looked at the difference between declare and define, where you declare something and where you define it. And C, things can only be defined once, but they can be declared all over the place. So you can all over the place say, this function's got this type signature, this function's got this type signature, this function's got this type signature, this function's got this type signature. But you better make sure that there's only one spot where you say, and the function is. And you can say, this thing's an int, this thing's an int, this thing's an int, in lots of different ways, in lots of different places. But you better make sure you only allocate memory for that variable. You only actually declare it, define it. Which is which? Which is which? You guys help me. Which is declare, which is define?
Declare allocates, define gives a value.
Declare allocates, define gives a value. Is that right? No, let's do it for functions first before we do it for memory things.
Okay. Well,
Doesn't define give you the definition of the item, which can only really be done once because it's universal to that item anyway?
Yeah, I'm pretty sure.
And declaring is saying, here it is.
Yeah, I think you can declare them multiple times for a function.
yeah, has to be the same.
Yeah. Declare is where you say what it's going to look like. So you give the type signature for it. Define is where you... So how will you give a function a value?
X equals 0.
Yeah, we know you say the function has this body, where you write the function out. Yeah. So we declare our functions in our .h files, and we define them in our .c files. Okay, then we looked at scope, just quickly, that a variable in one function is different to a variable in another function even if they've got the same name, and we looked at the idea of scope. We looked at .h files, and we looked at our first trap and pitfall. And we love traps and pitfalls, and C's got lots of them, so we love C. Two very, very similar things pronounced exactly the same way with completely different meanings. So it's very hard when you read your code out loud to even notice you've made a mistake. The difference between 1 equals and 2, classic blunder. I'm sure it'll be in the exam somewhere. What's that? It got into the Linux kernel, a mistake like that. Yeah, look, it's everywhere. It's just a mistake asking to happen.
Actually, it was malicious.
It was malicious. Oh, that's even funnier. Okay, the one formula you need to know. What was the one formula you need to know? Oh, I can't remember what it is. Does anyone remember? N times n plus 1 all over 2. What does that mean? The sum of all the numbers between 1 and n. Cool, well done. I better make sure you do need to know that. Who thinks they need to know that? Who does know that? Who still has to know that? Okay, so if you still don't know it, make sure you do know it, because there's bound to be a problem where you have to add things up, and the first time through the loop you do something once, and the second time you do it twice, and the next time you do it 3 times, and I'm going to say to you, how many times do you do it in total? So you're going to have to add that up. So do make sure you know that formula. Then is that not how you spell formula? That's how I spell formula. Formula. It's because I know Latin, and that's the Latin root. Recursion. We then introduced the concept of recursion, which hopefully sounds a bit familiar to top-down design to you. Because recursion is, how do you solve a problem by using the solution to a slightly smaller version of the same problem? Does that make sense? How do you solve a problem using the problem? So if you wanted to find factorial of 5, what other factorial would you relate it for to solve that problem? Yeah, how do you solve factorial 5 given factorial 4? How do you sort a whole list if you can sort 2 halves of the list? That's a recursive solution. Suppose you could sort 2 halves of the list. So I've got one sorted half here and one sorted half here. How do I solve the whole list?
You check the first and last elements and stick them together.
I put them together by doing an operation we call, not concatenate, merge. Merging 2 lists. Remember we did that? You got 2 lists, you sort each of the lists, you merge them together. That's recursion. Yeah? You sort the whole list by using a function that sorts part of the list. Recursion is really neat. And we saw recursion over and over again. Then we looked at other types. So other ways that C interpreted the bits that it stored in its memory. Up until then, we'd only been talking about ints, which we'd always assumed were like 32 bits long. But we saw that C could use its bits, and when you pulled the bits out, instead of saying this is a number, an integer, you could say other things. You could pull 2 of them out and say it's a long. Or, actually I think long was the same as int on my machine, was it? But on some machines they're different.
Maybe on 16-bit it's how long is 32-bit?
Maybe a 6, I'm sure longs, if we went back to an old 6, yeah, if we went back to an old 1086 or something like that. Yeah. If we went back to a really old chip, longs are probably different lengths to ints, but these days they're probably the same. But longs are probably longer. Longs on my machine I vaguely remember was 64, weren't they? Is that right? Does anyone remember? You don't need to know for the exam. You just need to know that you can take glumps of bits out, and what value you say those bits have depends on what type you think those bits represent. If you think they represent ints, you might say, oh, there's an int here and an int here. And if you think they represent longs, you might say, oh, that's one really enormously long int. And if you think they represent floating point numbers, you might say, oh, look at that, it's pi, I recognise it. And we looked at big endian and little endian. Does anyone remember the difference between big endian and little endian?
The eggs.
It's which end you eat, which end you crack when you eat the hard-boiled egg. An Intel machine is big endian or little endian? Little endian. What does that mean in terms of how do we, the egg analogy, how does that move over to an Intel machine, which is a little endian machine, what does that mean? If we've got a value that goes over more than 1 byte, like for example, I've got an int. How long is an int on my machine? 4 bytes, 32 bits. So those 32 bits are just filled with 1s and 0s and 1s and 0s and 1s and 0s and 1s and 0s and 0s and 1s. How do I take all those things and assemble them together to make a single enormously big number? Well, suppose this was 0, this was 0, this was 0, and this was 1. How am I going to assemble that? What number does that represent on my machine? What does it represent? If it was a big endian machine, big endian means the most significant part is here. So this is, what are these? Each of these stores a number between 0 and 256. If it was a big endian machine, we'd say the most important digit was stored here. So this is 0 lots of 256 to the power of 4, plus 0 lots of 256 to the power of 3. Oh no, I got that wrong. 0 lots of 256 to the power of 3, plus 0 lots of 256 to the power of 2, plus 0 lots of 256 to the power of 1, plus 1. And on a big endian machine, this stores a number 1. But on a little endian machine, it's the other way around. This is the least significant byte. So there's all these zeros, followed by all these zeros, followed by all these zeros, followed by a 1. So it would be like this. How many zeros are there? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1. This one is assembled first, and this one comes from here, and this one comes from 1, 2, 3, 4, 5, 6, right? From here, and this one goes to the end. That's a little endian machine. On a little endian machine, if they're stored like that in memory, they read like that when you call them a number. And the first guy you see is the least significant part. And you know, when we write numbers, we always put the least significant part on the right. In English, anyway. It's very confusing. Does anyone know a language where the most significant... Does everyone write to all... Is there anyone here from any country, or know of any country, where digits aren't actually the Arabic, like Hindu digits that I use?
India.
What do they do then? Little endian. Oh. You're making me look good. Thanks, Steve. It's good. My jokes suddenly seem, you know, amazingly funny. Yeah, look, I think everyone writes digits the same way, and I assume everyone writes them left to right the same way. Isn't that interesting? I think so, but I'd love to know differently. Does anyone know any country where they don't write digits in the same way? X86. The land of X86. So, in most countries, this number here, 1, 2, 3, 4, which is the most significant digit? The 1. This is, in most countries, this is 1,234. But in crazy land, there's no reason it has to be that way. It's just a convention we follow. It could be that the most significant digit's at this end. And that's 4,321. It's just a convention for how you write it. We've always written it one way, so it's even hard to imagine that there is a convention. We just do it without thinking. Yet in English, when we read, we go the other way. It's funny, when we're doing numbers, we go one way. When we read words, we go the other. So, in English, you read left to right. But you write right to left. You go the least significant bit first. That's 0, 1, 2, 3 if I'm going along. You see this is writing the number backwards? I know when we pronounce it most significant bit first. When I pronounce this number, here, I'll pronounce it in words. And you'll see I pronounce it big endian. 1,234. What did I say first? The most significant thing, the 1,000. If I was pronouncing it little endian, I'd pronounce it like this. 4 and 30 and 200 and 1,000. Yeah. Okay. So when you pronounce numbers, we pronounce them the same way we write them. But in terms of writing a program, you're always interested in going from little to big usually. Well, not always usually. So actually, they're sort of backwards. And if you wanted to extend the number... Anyway, this is a bit of a fruitless discussion. I believe we write numbers backwards to the way we speak. But of course, it's all definition. And that could be a good question in the exam. Debate whether really we're writing numbers backwards or forwards when we use big endian and little endian. Yes?
Some countries where they actually do write right to left, write the numbers the same way that we do.
Yes.
So that would be...
Very convenient. Yes.
Or if their brains work the same way we do, because it might just be the way our brains work, they actually write, stop writing, move their hand to a certain point, go backwards, and then...
Oh, I bet they don't do that. No, he was just debating about what happens in countries where writing actually goes right to left. Hey, does anyone who writes in a country where you go right to left? Yes, Sando? You write in a country where you go right to left? So when you write numbers, is that Turkish or something like that? Syrian. Okay, Syrian, Arabic. So if you're writing words from here, suppose I said, I went to the shop and I bought 1,024 oranges. Would you say, I went to the shop and I bought, would you then go here, 1,020, and go backwards? That's cool. That's amazing. So how do you know how much space to leave? Okay, but that is what people do. They actually do leave the right amount of space. Well, I'm amazed. Thank you. I'm going to write that down so I don't forget that. That's Syrian. It's Arabic.
All the Aramaic languages do that.
And they all, does anyone else speak Arabic? Does anyone write Arabic? Yeah, do you write Arabic? You can read, no, I want to know how you write it. I want to know when you're writing, if everyone jumps, yes.
It's also the same in Persian.
It's in Persian as well. So, and in Hebrew. So as you're going across, have you written in Persian? Yeah, you go across and then you jump and then you write backwards?
So you don't actually know how much space to leave.
That's amazing. And it's the same, you speak Hebrew?
Yeah.
Do you write Hebrew?
Yeah.
And it's, you're right, well done, Joseph. Well, I'm really impressed. Thank you, you've taught me something. Okay, let's go. Now, I've talked for an awfully long time, and yet, look, we're only up to week 3. I think we need a diversion. You know Japanese as well. Oh, you're just making me jealous now. I can't speak anything except English, and even then, not that. Terribly well.
English and x86.
English. Okay, hang on a sec, guys. I am impressed, but I'm not surprised that you guys have amazing skills. I'm just going to play something randomly from our soundtrack. Let's do a soundtrack revision of the week. What did we play in week 1? Hero. Does everyone remember Hero? It was very funny. No, we're only going to see a split second of it. This is like, you know, at the end of the Eurovision where they show a tiny little bit of each one.
You have to say all of it. You can't show us a bit.
Oh, no, I can only... Do you remember that? It's very funny. Okay, that was it. We're going to vote at the end. Shh. Then we did a sound check. We played some Viking music. What was that? I can't even remember what all these were. Oh, Dancing Queen.
Gotta play it.
Oh, it's a karaoke version. Yeah, they're our first pirates. And Viking music number 2. Oh, Simmerhorn. Oh.
These are Swedes.
Do you remember this? I didn't show the video. It's not a video clip, it's just a picture. That was cool. And then we did Bjorn is just a Viking and a tricky. Okay. Then we did something about how to learn skills. Oh yeah, we're talking about how you have to practice to learn your skills. And we did the skating one. Is that the firm? We looked at that amazing guy who could do those amazing things. I actually have some of that parkour stuff. You know that jumping around stuff? Oh, I should have shown you that. That just amazes me as well. Maybe that's the modern skating. Look at that. Wow. And trees and skating. It's got everything you need for this course. And then we did For Your Eyes Only. I can't remember why we did that. Oh yeah, because of the lector coding. No, there's a machine in that which was the same as the machine in the U559. Do you remember that? The story about the submarine that was sinking and they went back in and they grabbed the machine. And there's a James Bond film which has the same plot. For Your Eyes Only. That was an extension lecture, but there's no reason I can't show you the clip. Do I have the whole James Bond film here? No, it's just only got a little fragment. There's James Bond. He's getting in the helicopter. He's Dr. Evil, #1. There, he's flying the plane. And a very strange haircut. And then, here we go. Look, he's in a submarine or ship with the machine. It's not the lector coding machine, it's the attack. And then the machine sinks. And then the whole film's about how they try and get the machine back. And in week 4, don't forget to dereference your pointers. What happens if you don't dereference your pointers? What?
They didn't dereference their pointers right.
What was that one? Do you remember what that one was? Was that Zoolander? And it's gone? School for Ants? Oh no. Then we did, Tim did this a week I was away. That was quite awesome. That is so cool. We should do that. And then, all right, I think we've done enough distraction. Let's return to the real lecture. Yeah, we'll get back. You write down your votes. We'll all vote at the end. Shh, 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 shh. Oh, that was the break?
Really?
Yep. Did you want more of a break?
Yeah.
Oh. All right, you can have a quick break. You can have a break for as long as it takes me to assemble these potatoes into